Greetings and thanks for viewing this video. In this talk, I will give an overview of 3 worksheets that are in a planned sequence of about 5 worksheets. These worksheets are designed to provide a firm mathematical background in preparation for the study of quantum computing. The intended audience is high school students who know basic linear algebra, but who have not studied quantum physics and don't know the Dirac-Brocket notation. So you can see here that we have this worksheet, and in worksheet 1, we give an overview of inner product spaces, and this is going to be kind of a general overview that is not specific to finite dimensional spaces. And then in section 2, we will specialize to finite dimensional spaces and then start working on our explorations of the unitary matrix groups. And let's see what else. I mean, maybe it's better if I just go over each worksheet a little bit. So that's worksheet 1. And so in worksheet 1, we're introducing this computational exploration to get kids familiar with the matrix groups. And so when they actually look at gates in quantum computing, that'll be all completely familiar to them. In worksheet 2, we basically talk about the results of our explorations, namely we find lots of groups that are kind of very interesting, and the explorations are very interesting. So the idea is that in worksheet 1, we start very simple-mindedly by using the basic matrix formula for unitary matrices in U2, and we just start like trying to generate some of those. And we generate some of those and we try to complete them to groups, and then we try to extend those groups. And we keep going, right? And it turns out that this is really, quite an interesting little endeavor. And in worksheet 2, I sort of, talk about a lot of the explorations we found, the groups we found. And furthermore, down here at the bottom, I give you some new groups for students to work on, namely generated unknown group 128. That's the order of the group, generated unknown group 96, and generated unknown group 192. So those are the orders. And the idea is that basically we just keep extending. And what we want to do is we want to find like generators for these groups. So it's kind of a fun activity. And in the process, I create a bunch of code for this, including various kinds of set theoretic relations, operations, etc. And so, the kids can use these in together with the other code I've created in order to explore the groups. Okay, so so that's what 2 is about. And I'll kind of go over them a little bit more in a second, but I thought it's best if I go over all 3 first, since there's just a limited amount of time, and I don't want to miss out on one of them. So on worksheet 3, what we do now is we make connection, in this first section here with the material we did in worksheet 1, which is that linear algebra we did there, and we recapitulate a little bit of that, and then we also insert some material on the matrix exponential, some very interesting things, especially about quaternions, and namely that essentially you get an Euler formula for each quaternion, and some other interesting things about the exponential map. And we also then create a table in which we correlate all the kind of generators and groups we found in the exploration on worksheet 2. We correlate those with standard names for quantum gates. And then in section 4, we introduce tensor product spaces and also n-qubit spaces, gates, and circuits, and we have several examples of those. So up to this point of these 3 worksheets, this is all mathematics, right? So the idea is that it's kind of impenetrable if a student that doesn't know quantum mechanics, they don't know the science, they don't know the physics, they don't know the weirdness of quantum mechanics, and they also don't know the notation. So the idea is to base, their entry into studying quantum mechanics on, their foundation in linear algebra, and this is supposed to support that, these worksheets. Now, these are the first 3. There'll probably be at least 2 more. So in the next one, I'll do some more on examples of gates and circuits and some algorithms, and then some other interesting topics. That would be in worksheets 4 and 5. Okay, so let's go back to 1 then, and I'll take you through a little bit of that. So the first section, and let me make this bigger. So this is an outline of general inner product spaces over C complex numbers, and this is based upon the material in the fantastic book Hoffman and Kunze. Okay, for old people know what that is. A lot of people, other people should know too, because it's one of the best linear algebra books I think is ever written. There's so much wonderful stuff in there. In particular, the stuff on inner product spaces is terrific. I have reorganized it a little bit, but essentially, you know, this is, you know, a sketch of the material and an overview of the material that's in Hoffman and Kunze. So, you know, my intention is, and I mean like a firm foundation, so to take the kids through this material, you know, do exercises, etc. So this could take a while to get through that. And there's not a whole lot of, you know, computation going on right now. Basically, in this section, it's just, you know, going over the important points in inner product spaces where we don't assume, you know, finite dimensionality. So that's what I kind of gleaned out all the material that wasn't on finite dimensionality, just anticipating that some students may also want to go ahead and actually study quantum mechanics, in which there are, you know, non-finite dimensional spaces, infinite dimensional spaces. And so that's the material in this first section here, with all the usual definitions. I'm not going to go through all of it. I am going to highlight one of the theorems though, and that will be a theorem that I'm going to pull out of this section and then talk about in the next section when it's specialized. In this section now we specialize all the results in the first section to finite dimensional spaces, okay? So, you know, there's standard material here. I'm not going to go through all of it, like I said, but I do want to go to talk about this theorem right here. So this theorem is basically all the equivalences of unitary transformations in the case of finite dimensional spaces, also going to be, so those are linear, you know, unitary linear operators, and on finite dimensional vector spaces, they're going to be able to be represented as matrices, right? Now, the usual definition is not what I've done here. What I've done here is I've reorganized this in such a way, and it's real easy to do so, so that my definition of unitary is, you know, that the transformation, the operator maps unit vectors to unit vectors, okay? So that kind of really does more represent the notion of quote unquote unitary, right? And furthermore, what it does is that, you know, physicists have all these postulates that they want to invoke in order to justify using this formalism. And their very first postulate, namely that they're going to represent, you know, one qubit states, or a state of one qubit, using a vector in C2, right? So complex, you know, inner product space of, you know, of dimension 2, namely, right? So a two-dimensional space. Namely, once they make that assumption, then if they have any kind of a transformation that's going to be what they need, namely to map qubits, one qubit, you know, states to one qubit states, then that means that they have to map unit vectors to unit vectors, and in which case it's easy to show that that's just equivalent to all the other standard, you know, definitions, including that T preserves norms, that T preserves inner products, and that T is an inner product space isomorphism, and that, you know, bases get mapped to bases, and that the adjoint of the transformation is equal to its inverse. Okay, so basically what I'm saying here is that once you decide that you're going to, you know, like basically dig your heels into C2 and unit vectors in C2, and you're representing your physical objects in terms of unit vectors in C2, that means your transformations have to map unit vectors, in which case you don't have to assume all the other stuff, in which, you know, sometimes they like to talk about reversible, you know, physical processes, and, you know, how that's, you know, necessary to have unitary transformations because of that. But actually, once you've done all this, then you've already, you know, basically, you know, have everything you need. Okay, that's enough of that. So let's keep going. So there are lots of more, you know, wonderful details about unitary operators and normal operators, et cetera, all the basic stuff. Also, I introduced the general linear group here and some of its subgroups, the orthogonal group, the unitary group, the special orthogonal group, and the special unitary group. And then the main theorem and kind of the touchstone for all the computational explorations is this theorem right here. Basically, it's a characterization of the matrices in U2, and there they are, and also the matrices in SU2. Okay, so so once we have that theorem, then we can just kind of work with one of these matrices and start generating, you know, one of these forms and start generating matrices. So all you really need is you just need what the two complex numbers are, X and Y, and then you can generate the matrices. And I basically created some methods to do that. And so in the first, I'll just show you a little bit of this, and then I'm going to go on because there's kind of just a limited amount of time here that I want to do in this talk, and I'm about halfway through now. So what we're going to do is we're just effectively going to take the identity matrix, which is a unitary transformation, and then just take, you know, the one in the upper left-hand corner and just replace it by plus or minus 1 and plus or minus I, so that'll generate 4 more matrices. And when we do that, we'll get this, okay? And so the idea is we're just gonna explore these matrices, see what they're like, right? So then we're gonna do the same thing, only we're gonna put right, we're gonna hold, so what we did was, you know, using this matrix right here, we changed X, we let it be plus or minus 1, plus or minus I, and we had Y 0. Now we're gonna go the other way around. We're gonna let X be 0 and let Y be plus or minus 1 and I be plus or minus, sorry, and Y be plus or minus I. Okay, then we'll generate these. And then there's a very kind of, you know, interesting aspect of these two, which you probably already know already. These two sets of matrices we generated, it turns out that they're basically, they form the Quaternion, you know, finite group, subgroup of the unitary group, okay? Actually of the special unitary group, right? And so there's a bunch of little exercises that I've created in here in order to verify that for somebody who doesn't know any group theory or very little group theory at all. And so anyway, I'm not gonna, you know, click through all those. I will mention though that, you know, as I said up here, that please execute all the code below in sequence because some of it depends on, you know, the code above. So something is defined here so that if you just run down here and execute something that uses that, then if you haven't, you know, like executed the one above, it won't be defined. Anyway, so we go through all this kind of, this is kind of just an intuitive visual exploration, computational exploration. We go through all this stuff and we eventually get the Quaternion group. As we just noticed here, we showed that it was a group. And furthermore, you know, we basically can relate that to the standard form of the matrix for SU2. And we do that in the standard way. And then that sort of like gets us involved in thinking about the actual Quaternion, you know, division algebra. And so we write all that stuff down. Okay, so we're, you know, and there's a lot of wonderful detail in my opinion, you know, that students should know this stuff when they're studying this. And it's also, it's really interesting and fun. And also it's a good grounding in, you know, these matrices. Okay, so now the, you know, more of the computational exploration goes on here. And what we decide to do here is, okay, we have the Quaternion group, this GQ is what I'm calling it. And suppose we try to extend it by some matrix. And so I'm randomly, and maybe not so randomly, picking just a simple permutation matrix, which is 0, 1, 1, 0. And I'm going to throw it into that group and see what we generate. Okay, and then that's what all these exercises are about. And as you probably know, you know, when you get done with all that, we end up generating the Pauli group, which is a group of order 16. The Quaternion is a group of order 8. And so then I sort of like detail all that in a table here. And we're off and running with our various groups. Okay, then I have some software that I've developed here to like sort of explore these groups. And so for example, what we're gonna do is we're going to look at the group, the GQ group, which is the Quaternions. And we're gonna, if I just run this, it will basically take all the elements of the group and see what subgroup are generated by them. So, okay, so for example, you can see that you know, 801, and these are my names, right? 801 generates this group and it has various properties. It has an order portrait and it's effectively isomorphic to C4 and et cetera. Okay, and that's not surprising, right? And there's one that's isomorphic to C2. And of course, that's that matrix right there, -1, -1. Okay, so basically that's what we're doing. And this is what I want them to explore. I want this for the elements of the Pauli group, okay? And so that's some more examples of that. Then there's, you know, an exercise here and there's a couple projects here. And basically the projects are to continue the exploration. And I'll just click to the group names website real quickly here. Hopefully it will show up. And this is what I'm talking about. This is, you know, really kind of a fun and awesome place. You can, on many of them, they have like the subgroup lattice and lots of other properties, including the Partitioned subgroup, commutator, et cetera, lots of cool stuff. And so that also will be kind of a little, this is a little exploration and a little, mini group theory course in the middle of this too. And so what I did is, in the exploration that I did, is I effectively, all the names in this column right here on the left, those are all the unknown groups to me. And then these are over here are I correlated those using the group names website with the ones in this row right here, and I was able to identify what they are, right? And so it turns out that, of course, the Quaternions are Q8 on the group names website, and the matrices, or the poly group, is C4 circle D4, which is the central product of C4 and D4. Okay, so then there are different kinds of products here, so students have to go figure out what those products are, right? So, and that gives us something and a reason to talk about them. Okay, so there's that table. Then basically, I did the exploration myself, and there are many groups we found here, and one really interesting one is this, I'm calling it a super group because it's a super group of all the subgroups that are going to be below it. And so the idea is to find generators and generate all these things by continuing to extend. You can see that, where we started with Q8 right here, the Quaternions, then the poly group, and then we went, the next group I found was the wreath product of C4 on C2, which is a group of order 32. Okay, but in terms of this worksheet right here, effectively what I have this super group, or the group that's above all the ones below, that's basically all the ones below are subgroups of it. And I have effectively, we have 5 different groups of order 32, that's a subgroup of this group, which is order 64. And we have 7, different groups of order 16 that are subgroups. Okay, so those are all the ones I've included here, some version of them. Sometimes there are isomorphic copies, right? So here's an SD16 and another SD16. And, that's kind of the way it goes. So I'm thinking about now what I should do next. Well, let me just point out here that the way the software works that I've developed is basically we're taking generators, and I've named the generators, giving them Greek names. And sorry if I basically, stepped on somebody's toes about that, but I pretty much, just as I developed all this, I gave them names. And then I use those to generate the group. And this is the group, I already executed this. I don't want to do it right now. And so there's a group of order 64. And then what I do next is that in order to find the subgroups, like originally when I didn't know what this group was and I just generated it, I need to sort of get the group elements and use them singly and in pairs and in triples, et cetera, to try to generate the subgroups. And so that's what I do. I take this group that I generated using these 3 generators right here, and now I make it a bunch of generators. And how do I do that? Well, I basically create a bunch of pairs. Okay, so I pair off, and rho, by the way, sorry, I stepped on somebody's toes about this, but rho is my generic Greek letter. So basically I have a pair, a Greek letter and a name for each one of these, matrices in this group. And so, right, I have 64 of those. And then in order to explore, right, what I do is I execute these guys, right? And then I can look at all the, what's generated by single elements, what's generated by 2 elements, what's generated by 3 elements. And I have the times here for how long this would take for this group. Some of them are, longer than others. It's a pretty big group. But what I want to do is I'm just going to go see if I have enough time maybe to get there. So let me go ahead and look at the wreath product. Okay, so that's the next one above the poly group, which is what the first 2 in the first worksheet were Q8 and C4 circle D4. So let me just go, and I can also run that stuff a little bit. So let me close this up and go down to this first one, which is the wreath product. And so the generators I found for this one were what I call mu4 and kappa 1. And let me just go through this. I think this won't take very long in terms of execution time. It always seems longer when you're watching. Okay, so there's the pair, here's the group. And realize that when you're doing this, you don't know what group this is, right? I have now renamed them. I know what the generators are, so they're correlated, but they were unknown groups when I was first approaching when I did the first extension, right? So effectively, I'm extending stuff, right? I'm extending, using these two generators, the groups I already had. And so then what am I going to do? I'm going to pair these up with names here so that I can find out what the subgroups are. So that's the next thing I'm going to do is take that whole group I generated there, pair it up with names, okay? And then I can explore the subgroups. Okay. And basically, I'm just taking one element subgroups, but you can see combinatorially, right, it becomes a lot, and so some of these take a while. And one of the things that's interesting here is what's generated, and do the same thing for two generators, et cetera, are essentially, you end up getting the order of the generator you use, the order of the subgroup that you generated. You won't know the name when you're generating these for an unknown group, right? So that won't be printed out, but you will know the order portrait. Now, it turns out that the order portrait, these are all, these are all P groups of where P is 2, right? So this is like, this is the number of elements we have, 2 to the 0 order elements, number of elements we have order 2, right? So order 4, order 8. So that's what a order portrait is for these groups. And so you get those. And so what you can do then is you can use that information, right? And the group names website, right? To try to figure out, like, okay, what are the different subgroups, right? So this is apparently the same one down here. Now, it turns out that order 16, the order portraits aren't unique, right? So that you have to do something about that, right? You have to start paying attention. But it turns out in all the explorations I've done so far, that there have been a couple of conflicts, where you had the same order portrait, and I was able to sort of distinguish those by basically using my abelian method. So they can, like, the one conflict I had, one was abelian and one wasn't. Okay, so we really don't have a lot of time to go to the next one, but that's kind of the basic idea. And let's see. I know I'm kind of running out of time here, so let me just briefly go down and point to. So these are the new project challenges I've set for the kids. So here's a generated unknown group of order 128, generated unknown group of 96, generated unknown group of order 192, right? And so this is kind of a process by which they can, approach this. And I have is abelian matrix group here. I have these different methods that are in the code, in set matrix. So the matrix, right? So basically A is in the set of matrices, set matrix subset. So basically I have sets of matrices, right? So this is a subset relation tester for a set of matrices, and right, an equal tester and a union and an intersection and a minus for those. Now this very first one, I've given lots of hints, so I won't have time to go through it, but there are lots of hints here, and it basically gives you a sketch of how to approach the problem where you work back and forth, between, all you have is a generator. So you generate this unknown group, and then, when you run these different tests, like for example, I already ran these, right? So when you run these different tests, then you'll see that, for the known ones, you see all these order portraits, but now look at subgroup for order 16. You have the order portrait, but you don't know what the group is because it's a new one. So it turns out it's going to be C16, but that's kind of the way that goes. And that's why you need something more to help you figure out what they are, right? So, and now here's some of, where I'm using two generators. And so here's the whole group got generated. There's the 128 unknown group and more. And now here's one, a subgroup of order 64, okay? That's unknown because it's not named here, right? Oh, here's another one. So those are two different ones of order 64. So I know I have two different subgroups of order 64. So that gives me information, right? So I can look at the groups of order 128 that have certain properties. I can analyze them some more. I can use my various subset, my set theoretic, test and relations to determine how they're related to the groups I already have. Okay, and then I give kind of a complete description of, just thumbnail sketch of how to do that down here. That's worksheet 2. Now worksheet 3, as I said in Worksheet 3, I basically recapitulate some of the technical material that I had in Worksheet 1. Introduction to that, and some interesting results that can be, in my opinion, can be included here. Okay, so then there's a table here that has a lot of the basic quantum gates here, and I correlate those with the generators that we found in all our group explorations. Okay, so those are my names over here in this column, and these are the standard gate names. So I do that correlation, also mention, a subgroup that's generated, by some of those. And then there's a nice exercise here, and then the final section, and then this section right here is to help with this exercise. Okay, finally, we're here at the n-qubit tensor product state spaces and gates and circuits. So basically some standard stuff on tensor products. Everything is mulched together in one gigantic tensor product theorem here. And then we, of course, generate these tensor product spaces by using bases and taking their tensor products. And then I have a whole bunch of examples. Okay, let me just do one circuit here. So here's an example of three circuits, a NOT circuit, a C-NOT circuit, and a CC-NOT circuit, okay? And so basically I have images for that. I have, the matrices that correspond to those. And I'm emphasizing the fact that these so-called circuits, when you have V1 and V2 here, there's different ways to view this, but in order to make the connection with mathematics, you're thinking in terms of, okay, yeah, basically this is going to be the tensor product of these two states of the first qubit and the second qubit. And so when you apply these matrices, you're going to apply them, to the tensor product, okay, if you were to collect them all and multiply. And so here's an example of that. And so effectively what we did was, we did the NOT, which just switches, right? Basically it's, in a linear combination, it will switch the two basis vectors. And the C-NOT, in a linear combination, it will switch the last two basis vectors. And it basically conditions off the first character of the subscript, and etc. for the CC-NOT. CC-NOT is going to interchange the last two, in a linear combination, the last two basis vectors, and that conditions off the first two characters in the bit string that's naming the basis vector. Okay, so I've probably went way over time here. I'll go and edit this video, but that's the idea. And then here's some more interesting ones. And then, as I said, what we will do in the next couple of worksheets, we're going to do some more interesting problems having to do with, circuits themselves. And at this point, we have not done any quantum mechanics at all. There's no quantum physics involved at all. This is all completely mathematics. So, and the whole point is to give the students a basis in something they feel comfortable with, and then they'll be prepared to then delve into, quantum computing more deeply. Okay, thanks very much. And I'll be looking forward to your questions and comments at the conference.